So we've looked at fusion in the main sequence, the PP chain and the CNO cycle, two major processes. But what happens after that? How do we get the heavier stuff? How do we get the carbon, nitrogen, oxygen needed for the CNO cycle? In the first place, for example, how do we get heavy stuff like uranium? Otherwise uranium just wouldn't exist. Well, a couple of things. There's basically fusion, like regular fusion. What would happen? Well, imagine a star's been producing loads of hydrogen, so helium from hydrogen for its whole life. There'd be loads of helium around. Helium and hydrogen could combine, of course, but a particularly common process is helium, which of course would make beryllium. At the end of its life, there's loads of helium, and of course the helium goes to the middle of a star, the bottom of a star. So the most likely thing for anything to get hit by, of course, let's put some numbers in here, is helium. So that beryllium, there's a decent chance it'll get hit by helium. So it's sort of going up by 2 every time, which of course would make it carbon, which could then be used in the CNO cycle. If we added helium to carbon, again it would go up by 2. It would make oxygen, and that's why there's oxygen. And it could go heavier and heavier. You're supposed to just generally know about this process. Think about a star here. There's the core, and there will be layers of it, depending on how big it is. If it goes to the red giant phase, which most will, there'll be layers of this. They're getting hotter and denser, and there'll be more of the heavier elements. So initially, you have helium, you get some beryllium going on here. Then you get beryllium fusion. The beryllium will generally sink to the bottom here, and it might form carbon. And then the carbon would fuse with some helium, make some oxygen. So as you went deeper and deeper, like an onion, you get these denser layers. If it's a very heavy star, before it goes supernova, then you would get really heavy stuff. You get uranium at the end. Of course, this just makes the even numbers. So how might we change to some other elements? Well, neutron capture, because there are bound to be some neutrons floating around. So neutron capture, and there are two kinds of this, the S process and the R process. So it has actually to contrast these two before. Firstly, they stand for slow and quick or rapid, obviously rapid process. So there's bound to be some neutrons flying around. So occasionally they're going to hit an isotope. So in the slow process, something would get a neutron, and then it would have time to decay. Generally, if you have an isotope, call it X, I don't mean xenon, that'd be Xe, wouldn't it? Gains a neutron, then it would become, let's say, Y, with just an extra number here, just +1 here. It could keep doing that, of course, quickly or slowly. So if it's slow, then there's time for decay at every step. If it's now getting neutron heavy, it's likely to convert some of those neutrons into protons. If it does that, it would also make an electron and an antineutrino, you know from topic 7. So then, if it changes that neutron into a proton, then, let's go down here, sorry. Neutron to a proton, then let's call it Z. So now it's gained 1 here, it's still gained 1 there, same mass, and of course we've got the electron and the antineutrino. So there's a way in which the proton number and the mass number can go up by 1. So if you had oxygen here or carbon here, for example, you get to all the odd numbers as well. If it's the rapid process, then it would just keep gaining neutrons. So if there's loads and loads of neutrons around, it's rapid just means there's no time to decay. So it would keep getting to heavier and heavier isotopes until the half-life got so small that it has to decay, basically. We have a very short half-life. So compare the S process and R process. In summary, it's simply neutron capture. But with the slow process, it's slow enough that you'll get decay along the way, which basically means the proton number's going up. If it's R process, that means you just keep capturing neutron after neutron. The mass number will shoot up a lot before the proton number catches up.